Section 1.7 Linear Independence. A set of vectors v1 to vp in Rn is said to be linearly independent if the homogeneous vector equation x1 v1 and up to xp vp linear combination is 0, has only the trivial solution. That means that the solution of this vector equation is 0 values. Then we say the set of vectors is linearly independent. Otherwise, we say it is linearly dependent. More precisely, we can say this one. If there exists weights C1 to Cp, not all 0, at least one is non-zero, such that this combination is 0. So the equation has a non-trivial solution, then the set of vectors is linearly dependent. Okay. Determine if the set is linearly independent. Mathematics begins with a definition. So we'll try to start with that linear combination equals 0 and try to find the solution. Okay, here we start with x1 v1 plus x2 v2 equal 0. If x1 is multiplied here, then the vector becomes now 3x1 and 0. For the second part, x2 is multiplied, then that will become 0 and 5 x2. So that's the 0. Okay. Now for the left side, and if we combine, then that is 3x1 and the second one must be 5x2. Okay, that is 0. That implies that x1 must be 0 and x2 also must be 0. So for this vector equation, the only solution is this trivial solution. So these two vectors are linearly independent. Okay. Now, how about this one? For that one, we can see easily v1 is same as 3 times of v2. It can be written in this way: 1 times v1 and plus here minus 3 times v2 equal 0. So we have here non-trivial solution 1 and minus 3. That is C1, C2 are 1 and minus 3 respectively, and the combination is 0. So it is linearly dependent. Once linearly independent, then here one vector cannot be made from the other. Here this vector cannot be made from this one. However, here now linearly dependent, then a vector can be made from the other, like in this equation. v1 is 3 times of v2, and also v2 is 1/3 of v1, right? That A is the collection of vectors v1 to vp are now collected to make a matrix. Then the matrification Ax equals 0 is equivalent to this vector equation. We already know that. And columns of A are linearly independent if and only if Ax equals 0 has only the trivial solution. It's the same as that this vector equation has only the trivial solution. Now, Ax equals 0 has no free variable to get only the trivial solution, A should not have, this system should not have a free variable. And every column of A is a PV column, so that free variables cannot happen, right? So this statement, that one, and this final one are all equivalent. Columns of A are linearly dependent if and only if the homogeneous equation has non-trivial solution. And it's true, and that is also equivalent to this statement. Ax equals 0 has at least one free variable, so that it can have non-trivial solutions. A has at least one non-PV column. Once A has at least one non-PV column, then corresponding column is a free variable, right? So all three are equivalent. Okay, let's see this example. Determine if the vectors are linearly independent. Okay, for this one, again, same A, and start with the definition, and V1, V2, then start with x1, V1 plus x2, V2 equal 0. Then the left-hand side can be written in this way. That is now, okay, x1. Here, the first component will be x1, and second component must be x2, and final one is 0, then is 0. That implies that x1 and x2 are simultaneous 0. So the vector equation, only the solution is the trivial solution. So they are linearly independent. Okay, and also here, once you start with now that one, every column of A is PV column. Once you collect these two vectors, then this will be pivot and that will be pivot for the resulting matrix A. So every column has pivot, so that it must be linearly independent. Now again, for that one, if we are using this one, then now we collect them as a matrix. Then now A has at least one non-PV column. It's quite clear. This is PV column because this is pivot, 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 but that is not PV column. So A has at least one non-PV column. So these four vectors, the set of these four vectors must be linearly dependent. If you begin with the definition and linear combination equals 0, then you can find non-trivial solutions. Okay, but anyway, by using this statement here, you can easily check that this set of these vectors is linearly dependent. Okay. Okay. Determine if the vectors are linearly independent. Okay. So we'll check that along with this last statement. Once every column in A is a PV column, then it must be linearly independent, right? So start, okay. So we make a matrix A. So assume we collect them in a matrix. Then from this one, now we try to row change. Then that is now, okay, this is 0, so that we move this one on the top. So that is here 2, 0, 3, and now that is now 0, 0, minus 1, and the last one is 3 a minus a and 1. Okay, from here, now let's eliminate this one. Then that is now 2, 0, 3. Okay, that is 0, 0, minus 1. And then, okay, that is 3 over 2 is multiplied and subtracted. Then that will be 0. And that is minus 8 the same. And, okay, now that will be 9 over 2 is subtracted, so that minus 7 over 2. Okay, now by changing row here, 2, 0, 3, and 0, minus 8, and minus 7 over 2, and 0, 0, minus 1, we can see that every column has a pivot. So every column of A is a pivot column, so that the column vectors must be linearly independent, right? So columns of this matrix must be linearly independent. So they are linearly independent, okay? Determine if the vectors are linearly independent. Now, if we are using the same technique, so collect these vectors as a matrix, then there are 4 columns. If we apply elementary row operations, then here maximum possible number of pivots must be 3, because there are only 3 rows, so that this last column cannot have a pivot. So that is at least 1 non-pivot column. That means that collection of these vectors is linearly dependent. The A has at least 1 non-pivot column. Then here, the columns of A are linearly dependent, right? So you can easily see that this set of these vectors is linearly dependent. Now you can use also the definition, and x1 v1 plus x2 v2, x3 v3 plus x4 v4 equals 0, and you can make an augmented matrix and apply elementary row operations. Then anyway, you will get the same conclusion. Okay. In the above example, vectors are in Rn and 3. The number of vectors P is 4. Like this one, once P, number of vectors is larger than the dimension, then the vectors must be linearly dependent, because the corresponding matrix should have at least 1 non-pivot column. So the set of vectors must be linearly dependent. Here we write down the observation into this theorem. The set of vectors v1 to vp in Rn is linearly dependent if the number of vectors is larger than the dimension n. Here we have a proof, but the proof is based on the comment I made. Okay. When p is larger than n, there are more variables than equations. This implies there is at least 1 free variable, which in turn means that there is a non-trivial solution. Okay. Okay. Okay, here, find the value of h so that the vectors are linearly independent. Okay, so we collect them as a matrix. Now you can imagine easily the matrix, just 3 columns, and here from the imagined matrix, now to get the echelon form, maybe we can move this one on the top. So 1, minus 3 and 3, and okay, we write down here 3 minus 6 and 9. You can also apply 1/3 the scaling, but anyway, and minus 6 and 4 and h. Okay, from this one, and 1 minus 3 and 3, and then now 3 times subtracted, then that will be 0. 3 times subtracted, so that will be here, okay, 3, and 3 times subtracted, so that will make a 0. Right? Okay, and then 6 times added, there's a 0. 6 times added, so that 18 is subtracted, so that minus 14. And here 6 times subtracted, 6 times added, right? 6 times added, so that must be h plus 18, right? Okay. Now here we can make a scale, and that can be subtracted, so that here we have, and 1 minus 3 and 3, 0, 1, 0, and 0, 0, and h plus 18. Okay, we want to find the value h so that the vectors here are linearly independent. To be linearly independent, the matrix should have pivots in each column, so that must be pivot, that must pivot, that must be pivot, which means that h plus 18 should not be 0. This should be non-zero. Then each column is a pivot column, so that these 3 vectors are linearly independent, right? So h is not minus 18, then they are linearly independent. Okay, we revisit the problem. Find the value of h so that C is in span AB. Now, we right now, these whole 3 vectors are matrix. Here, in this problem, C is in span AB. These first 2 columns, vectors, is that now x1, A plus x2, B must be C. And now, and so that we have to find h such that this vector equation has at least one solution. So when we try to figure it out, and we should start with augmented matrix, but the corresponding augmented matrix must be same as this one. But now the last column is from right side. Okay. In order to have a solution, and now this should not be pivot, which means that here h plus 18 must be 0. Then this linear system will have a non-trivial solution, and so that here C must be in span of AB. Okay. Okay, so here the solution for the problem is h plus 18 equal 0. Okay, so here h must be minus 18, right? Okay, now we'll try to determine by inspection if the vectors are linearly dependent. Okay, is it linearly dependent? Why? The reason is this one, the first one, plus twice of the second one becomes the third one, so they are linearly dependent. Okay. Now for this one, it must be linearly dependent. Zero vector. Once the set of vectors include a zero vector, then it must be linearly dependent. The reason is that there's v1, v2, v3. Then we start with 0 v1 plus 0 v2, and for arbitrarily constant, for example, x3 and zero vector must be 0. So that this is non-zero, so that this it has non-trivial solution, 0, 0, some arbitrary number, so that along with a non-trivial solution, the combination is 0, so that these 30 vectors are linearly dependent. So here the conclusion is that once a zero vector is, the zero vector is included in the set, then the set of vectors must be linearly dependent. Okay, for this last one, and v2 is apparently 3 times of v1, so that this set is linearly dependent, right? Okay, here, now S is a collection of vectors. If S contains the zero vector, then it is always linearly dependent. A vector in, okay, S is a linear combination of other vectors in S, if and only if S is linearly dependent. Once the set is linearly dependent, then one of them is combination of the others. You can do it so that these two are equivalent, so that a vector in S is a linear combination of other vectors. Then the set of vectors is linearly dependent. Okay. Now we'll go to true or false problem. And okay, let's say the columns of any 3x4 matrix are linearly dependent. Is it true? It is true. The reason is here only 3 and in each column in 3 dimension, and that is 4 columns, so that and last column, at least the last column will be non-PV column, so that the matrix has at least one non-PV column, so the columns must be linearly dependent. So it is true if U and V are linearly independent, and if UVW is linearly dependent, then W must be in span of U and V. Is it true? Yeah, it is true. You can figure out quite easily. If you start with the matrix, corresponding matrix U, V, W, then from here you can say that now linearly independent means these two are linearly independent, means that here it is pivot in the first column, and the second one it is pivot another one. But now UVW is linearly dependent, means that here there's no further pivot in this third column. So that here now we have at least one free variable, or we have at least one non-pivot column. And in the case, the third column can be made by using this first two, so that W is a linear combination of U and V. That means that now we may consider the third column as right side in the beginning, then it has a solution, right? So that W is in span of U and V. That means W is a linear combination of U and V, okay? So it is true. Two vectors are linearly dependent if and only if they lie on a line through the origin. Is it true? Yeah, it is true. Here, two vectors can be here arbitrary, so that one of them, at least one of them, can be zero, and both are non-zero, or they are on the same line. However, in any case, here they lie on a line through the origin if they are linearly dependent. Linearly dependent means that one vector can be made from the other one. So that essentially, they can be put on one line through the origin. Okay. In any case, is true. Okay, here the columns of a matrix A are linearly independent if the equation AX equals 0 has the trivial solution. Is true? Is it true? It seems true. However, you have to be a little bit careful. AX equals 0 has always the trivial solution, so that this part after if has no meaning because it has always the trivial solution. So eventually, the statement, whole statement is saying that the columns of matrix A are linearly independent always. Okay, so to make it true, you have to change this portion. If the equation has only the trivial solution, once the solution is only the trivial solution, then that means that there's no free variable. That means every column of the matrix is a pivot column, so they are linearly independent, right? So that if you put here only, then it is true. Okay, that's the end of the section. Thank you.